Dvorkin from Harvard. Cora will talk about unlocking dark matter physics out of astrophysical data sets. So thanks, Matthias, to you, and Cora, over to you.
Thank you. Could I ask you to make the other Cora Dvorkin a host?
Yeah, just a second. I have to find the other Cora. I found the other Cora.
Okay, there.
So we have a split personality. Okay.
No. we have double the women power. Let's say that.
1 second, and let me make this so that it doesn't bother me. Yeah, so do you see my screen all well? No rectangles or anything there?
Perfect.
Okay, great. Let me see, it's 2:44 and I have 30 minutes. Great. Okay, well, so let me start by thanking very much for the invitation and saying that I hope everyone is doing well. I'm happy to see many familiar faces, at least virtually and hopefully in person soon. So today in these 30 minutes that I have, I will tell you about some of our efforts with my research group to unlock dark matter physics out of astrophysical data sets. And in particular, I will be focusing on the small scales, much smaller than what Matthias has talked about. Oops. 1 second, there. So here is where we stand in cosmology today. We have a standard model of cosmology known as lambda CDM, and this model has been extremely successful on cosmological scales among a wide array of different observables, from the CMB, temperature and polarization fluctuations, to the clustering of matter, as Matthias talked about, and measurements of the expansion history of the universe. So here I'm showing you the matter power spectrum as a function of wave number. And you can see that this plot over here, it's a log-log plot, and it covers 4 orders of magnitude on each of these axes. The black line over here shows the predictions of our lambda CDM standard model. And each of the data points in color here is a measurement interpreted within the context of this model as a measurement of the power spectrum. So what's interesting about this figure is that it is spanning 14 billion years of history. It's spanning 4 orders of magnitude in length scales and a wide variety of cosmological probes. And we can see how the lambda CDM model fits them all beautifully. So in the past few decades, we have measured the large-scale structure of the universe very accurately with many different probes, the CMB and galaxy surveys, among others. And this has allowed us to put precision level limits on different kinds of dark matter scenarios. On smaller scales, however, there is a lot of structure, but it is not as well understood. Furthermore, many dark matter scenarios that agree at large scales, mainly by construction, show differences at small scales. So observations at the smallest scales provide fertile grounds for testing different dark matter theories. And so because we know structure formation is hierarchical, we expect an abundance of structure within dark matter halos. In particular, in the cold dark matter scenario, for example, we expect a high abundance of substructure compared to other dark matter theories. And this can be seen in this plot in the left over here that I took from one of Andrei Kravtsov's papers, where we see the predicted dark matter density for a Milky Way size halo from a high resolution embodied simulation. And we can see that there is a lot of structure within the halo. And one of the things that we have been analyzing with my group is how to tie these structures to dark matter theories. Moreover, we know actually that these structures exist because we have actually observed them. On the right here, I'm showing you a map from last year from the Dark Energy Survey collaboration, DES, of observed Milky Way satellite galaxies, meaning small galaxies that are virially bound to the Milky Way. So as an example of the effect of different dark matter models on subgalactic scales, I'm showing here 2 different projected dark matter densities. One coming from an embodied simulation in a CDM scenario over here. And on the right over here, I'm showing a simulation with the same initial conditions, but including now some exotic dark matter microphysics that results in dark matter clumps, which are more susceptible to tidal stripping. So you can see by eye already that there is a lot more structure in the CDM model than there is in the exotic dark matter scenario. And this is just an example to illustrate the fact that exotic dark matter physics can lead to interesting phenomenology that is observably different from CDM at these scales. And so the idea that I will be telling you about is to probe dark matter fluctuations on small scales. And by this now I mean kiloparsec scales that are, again, much smaller than the scales Matthias was talking about, to falsify or corroborate the CDM paradigm. And so our goal will be to map the distribution of dark matter on small scales in halos of galaxies. And our tool for this will be strong gravitational lensing. And in case there are people who don't have this fresh in their minds, let me give you a review in one slide of gravitational lensing. So basically, we will have a background source at some high redshift. And in our case, this will be a galaxy. And there will be a foreground galaxy between us and the background source that deflects the light because of its gravitational field. So from our perspective, we will see these extended arcs that you can see here. And so the idea will be to use these images to see if the lensing galaxy is clumpy or smooth. And so one can map an image back to the source plane by a deflection angle field, which is the gradient of the gravitational potential of the main galaxy acting as a lens. And the idea that has been suggested almost 20 years ago already by Mao and Schneider is that substructure in the halos of galaxies, what I will be calling subhalos, will locally perturb lens images. So by looking at the residual between the image predicted by modeling the lens galaxy as a smooth mass and what is actually observed, we can infer the presence of these subhalos. And the advantage relative to other methods for detecting dark matter is that we do not need to assume a specific coupling between the standard model and the dark matter, in contrast to, for example, direct detection experiments or indirect detection experiments and colliders. And so in this sense, I say that we are model independent. Furthermore, we will be focusing on the lowest mass subhalos, which are largely devoid of stars. So detecting them with a gravitational technique is the only possibility that we have, since these subhalos cannot be seen directly. And so with my group, we have done work in this arena following two different and complementary approaches. The first approach is a direct detection approach, where our goal is to resolve individual, more massive perturbers and from there infer their properties. And the second approach is a statistical detection approach, where we want to marginalize over individual subhalo properties to learn about the subhalo population characteristics. And so here we will be exploiting the steepness of the subhalo mass function slope. Basically, this is the expectation that we have a huge population of these very low mass subhalos to try to statistically detect their collective perturbation on images. So let me start here by talking about the direct detection approach. And once we build intuition, I will move on to the statistical detection approach. So now we will have the same picture as before, but now we will be adding a subhalo or more than one in the halo of the lens galaxy. And we will look for a small deflection of the light as the light from the source crosses the lens. So the quintessential method for direct detection of subhalos is known as gravitational imaging. And much like what it was proposed by Mao and Schneider, the underlying principle is that if you have some dark clump lying close to an imaging projection, there might be some visible distortion that you can try to reconstruct. This figure that I took from a paper by Simona Veghetti and collaborators very nicely illustrates the pipeline that goes behind this. Basically, we start from some data, a strong lens galaxy in our case, and we have to model the smooth component and the object doing the lensing, assuming that there are no dark matter clumps. And we also need to reconstruct the source. Once we have these two ingredients, we can forward model the source to obtain the smooth model image. And so by trying to minimize the residual between the data and the model, we can ultimately reconstruct the surface mass density that gave rise to the original data set. This is what we call convergence field. And so in this particular case, we can see that the reconstructed mass density has an overdensity that you can see here. And this was a 10 to 12 sigma claim detection of a dark matter clump at this particular position in the image. Now, so far using this method, there have been a few detections of subhalos in the order of 10 to the 9 solar masses from about 30 images analyzed, okay, in the order of tens of images. But I want to emphasize here is that this is a very computationally expensive process, and it can take up to months to analyze a single system. So if you have tens of images to analyze, that's okay. But in the next few years, we expect tens of thousands of these lenses to become available for this type of science through, for example, the Vera Rubin Observatory, formerly known as LSST, and other experiments, in addition to further follow-ups, for example, by HST or the ELT, etc., etc. So, in fact, there are already many recently discovered by DES that are waiting for follow-ups. And this is great, since this vast increase in sample sizes will provide much stronger constraints on dark matter. But obviously, it is unsustainable to take months to analyze each system. So what motivated us, together with my former PhD student, Ana Diaz-Rivero, was the following question. Can we automate a procedure like direct detection using convolutional neural networks, making this process much faster and circumventing the step of macro modeling? And if we understood the sensitivity of our machine learning model well enough, we could still combine detections and non-detections to probe different dark matter scenarios. And so the costly step in our procedure was to simulate high-fidelity strong lens images. This is an example of the individual components that went into simulating the final image. By the way, we use for this publicly available code called Lenstronomy that was mainly developed by Simon Birer, who is a postdoc at Stanford, and this is a fantastic code. So here we vary the macro model and the source together with the subhalo population in every image. And there are many degeneracies between these parameters, so in principle, it was not obvious at all that a network could learn something. For the source, we model it as a superposition of different clamps. We vary the ellipticity and the position of the host relative to the source. We had images with and without substructure. We convolved the images with the Gaussian PSF, and we added Poisson noise. So, and we also tested for correlated noise, basically to mimic the process of drizzling. And so what we did is we turned the problem into a binary classification task. We asked the question, for what subhalo masses is the network able to recognize the lens as having subhalos versus not having any? And in this way, we could identify promising candidates. And basically, since most of images analyzed with gravitational imaging yield non-detections, this could cut down analysis time and resources by a large factor. And so our expectation was that for very low masses, the network would not be able to detect anything. But if the subhalos were massive enough, the network would be able to detect them analogously to what happens in direct detection methods. So we simulated subhalo populations, fixing either the number of subhalos or the fraction of mass in substructure, but anyway, both gave us very similar results. This is the result with a very simple architecture. We found for realistic levels of noise that we could be sensitive to subhalos with masses around 10 to the 9 solar masses, comparable to the numbers cited in the literature for real detections, even in the presence of correlated noise. And so these results were very promising since they show that we can accelerate the process of discovery by many orders of magnitude, from months to much less than a second, obviously once the network is trained. So this was done for the first time in the literature for substructure as a proof of principle, but of course, you could get even better results by further optimizing your architecture. We used a very simple architecture in this work. So this is what we did next. We took the problem a step further and tried to cut the middleman entirely. We tried to convert the entire detection pipeline into an image segmentation task. Image segmentation is the problem of taking an image and trying to understand what the individual components that make up this image are. And let me mention that this was work done with my postdoc, Brian Ostiek. So to do this, we used a network architecture called UNet. UNets are networks well known for their success on, well, at the time, only on image segmentation in biomedical research and perhaps some other related fields, but now they have become more and more popular. So here we taught the network to reconstruct the convergence field or surface mass density by classifying every single pixel in the image as belonging to the background, the main lens, or one of the various subhalo mass classes that we define. The input was a strong lens image and the output was the probability for each class. And so here I'm showing you confusion matrices for two cases with different noise corresponding to different number of orbits with the Hubble Space Telescope, which tells us, this tells us that for a given class, what is that type of pixel more often predicted to be. And so, of course, we see that the network struggles to find the lower mass subhalos, and this is because of the level of noise. The level of noise for this case is just above the pixel brightness changes due to the presence of these subhalos. They're very small, they're very light. And so we provided an exact mapping in the paper that helps us understand exactly where we lose sensitivity. So we understand very well why it happens here or here for this case, but we also see that it does fairly well for subhalos above 10 to the 9 solar masses, which are again numbers comparable to the ones cited in the literature using standard methods. Moreover, we then show that the network can actually find not just one subhalo at a time, as it was trained for actually, but in fact, it can find a lot at the time. And on the left, there is one such example. Of course, it misses also many of them, but here you can see one such example. And we can now combine many of these images to place constraints on the logarithmic slope of the subhalo mass function, which again can give us insight on the nature of dark matter. And we can see here how combining more and more images, of course, the error bars get reduced. And we can see that, for example, when you use 1,000 images, we get about 10% error bars. So this is quite exciting. In fact, let me advertise this new institute that we started last year. I joined forces last year with my colleagues in various disciplines of physics and computer science at MIT, Harvard, Northeastern, and Tufts, and we started a new NSF-funded AI center that we call IAIFI, which stands for Institute for Artificial Intelligence and Fundamental Interactions, where I'm currently the Harvard representative at the Institute board. So it is one of, I feel obliged to advertise this and to tell you that we have our colloquia on Fridays at 2 p.m. Eastern time. Everyone is welcome to attend those. So if you go to this website, you can find all the information there. Okay, so let me switch gears now. I have 15 minutes left, great. So, and talk about the statistical techniques where we marginalize over the individual subhalo properties to obtain population characteristics. And the actual statistical observable that I will be talking about is called the convergence power spectrum. And the convergence, again, is the surface mass density. So the convergence power spectrum is particularly attractive for the task that we have at hand because it provides a bridge between what we observe, a strong lens image, and what we want to learn something about dark matter theories or about the nature of dark matter. And the way that this is done is by the fact that the convergence power spectrum can relate length scales, basically the deflection vectors on the lens plane caused by whatever is doing the lensing, to a mass scale, which is what dark matter theories are actually predicting, the halo or the subhalo mass function. So the convergence power spectrum is a nice bridge between the two sides of this diagram. So let me start by considering the limit in which all the perturbers are substructure that live in the lens. And once we build intuition and we understand how different microphysical properties of dark matter get imprinted in this observable, we can move on to the much more general and complicated case of a full 3D distribution of perturbers. So in a paper, again with Anna and Francis Yancey-Racine, a former postdoc at Harvard, who is now a professor at University of New Mexico, we developed basically a general formalism to study, in principle, the endpoint correlation function of the convergence field, but we started from the power spectrum. So The idea is that if we have a lot of substructure, the perturbations will look very close to Gaussian, the central limit theorem will kick in, and most of the information should be in the power spectrum. So we model the convergence field as a substructure component superimposed on a smoothly varying background density profile of the host. And so here the convergence field of the substructure depends on the substructure position, the mass, and the intrinsic properties that might determine the density profile. And so we proposed a change of language, moving away from talking about subhalos, and instead we propose to talk about the correlation function of the projected density field. And the advantage is that we don't need to define now what we mean or don't mean by a subhalo, as is generally done in the literature, and it can be quite ambiguous sometimes. So we started from first principles. This has been done for the large scale structure a long time ago. And since I was more familiar with this area when I started working on this, I applied the same kind of philosophy, but for smaller scales. So we will describe our power spectrum in terms of what we call a one subhalo term, analogous to the one halo term, which basically arises from ensemble averaging over the spatial distribution of a single subhalo, and a two subhalo term, again, analogously to the two halo term, which arises from averaging over pairs of distinct subhalos. And so here we'll be taking integrals over probabilities of the mass, the intrinsic properties, and the spatial distribution within the host. So here's our power spectrum. I'm showing here the one subhalo term. For the remaining of the talk, I will be ignoring the two subhalo term. Ask me at the end if you're interested, but basically it kicks in at very large scales. So we can see that for the power spectrum, the power spectrum is mainly described by three quantities. At low K, we have a plateau, a constant amplitude. Basically, we are probing scales that are much larger than any subhalo in the system. So at these very large scales, all the subhalos are essentially point masses, and the Fourier transform of that is white noise. And the amplitude of this plateau depends on the average abundance of substructure as well as some mass moments, as you can see here. As we move to smaller scales to the right, we have a turnover scale given by tidal interactions of the largest subhalos in the lens galaxy. And if we keep moving to even smaller scales over here, we reach an asymptotic regime where the power spectrum asymptotes to a constant power law. And this slope here reflects the properties of the inner density profile of subhalos that you're seeing here. It reflects the properties over here, which will be different for different dark matter scenarios. In particular, for an NFW profile used to describe the CDM scenario, this goes as 1 over k to the 4th. If we now have a non-trivial dark matter scenario, the density profile will change. Here we took as an example a self-interacting dark matter scenario, or SIDM. It has been shown that this scenario gives rise to a chord profile, as we can see here. You see in this green line over here, we see a chord profile. And now we see that at small scales, we change the slope, which again reflects the fact that the subhalos inner density profile looks different in this model. The slope now goes as 1 over k to the 8 instead of 1 over k to the 4. So here we have a promising theoretical prediction to distinguish between different dark matter scenarios. But notice that these scales are extremely small scales, and this is going to be hard in the near future. But what I will do now is I will discuss what we found out later, which is that if we add redshift information, we can actually look at much larger scale, well, larger, not much larger, but larger scales that are actually going to be accessible by near future experiments, and we can use this to distinguish different dark matter scenarios. So here I will briefly discuss the redshift evolution of these observables. On the left here, I'm showing the evolution as a function of redshift of the power spectrum in a CDM scenario. You can see that as we go up here, the different lines, I'm decreasing the redshift. So we evolve in time. The evolution here is quite intuitive. We see that as we evolve in time, the amplitude is increasing, and this is because we are accreting more and more substructure as time goes on. Here on the right, I'm showing you the same thing, but for an exotic dark matter scenario, which includes, in this particular case, These, by the way, are simulations that were run by Mark Vogelsberger and collaborators at MIT. These simulations include a low mass cutoff in the initial power spectrum and dark matter self-interactions, which have the effect to make the subhalos less concentrated and therefore more likely to be tidally disrupted. So you can see this reflected in the fact that the amplitude got stalled now between redshift of 0.5 and 0, where the increase in accretion in substructure is being compensated by the fact that a lot of substructure is destroyed. And this reduction of the effective subhalo mass at lower redshifts leads to a net transfer of power from larger scales to smaller scales in the power spectrum, as we can see here in the change in the power spectrum slope for wave numbers greater than about 2 inverse kiloparsecs compared to lambda CDM. So if you see these two slopes and these two slopes, we can see a change in slope as we evolve in redshift for these scales in the case of an exotic dark matter scenario. And note that these scales now are accessible by near future experiments. So let me say a few words about line of sight halos. So we just saw that the convergence power spectrum of subhalos, and by this I mean the substructure within the halo of the lensing galaxy, this is a promising observable to study dark matter. However, the distances involved in strong lensing systems are vast, and we expect that the relevant volume to contain line of sight halos that are not associated with the main lens. So recently, in work carried out by my group and collaborators at Berkeley, in particular, I want to mention two of my graduate students who led this paper, Chan Sengul and Arthur Sang. We developed a formalism to calculate the effect of line of sight halos as an effective convergence power spectrum. And so now, instead of having a single lens plane at some redshift, we can have any number of lens planes corresponding to the different line of sight halos. And instead of using the vanilla lens equation, we now use a recursive lens equation, which couples the angular deflections of successive lens planes. And so by assuming that the perturbations due to the line of sight halos are small, we show that they can be projected onto the main lens plane as effective subhalos. And we tested our formalism by simulating lensing systems using the full multi-plane lens equation and found excellent agreement with our analytical predictions. But basically, we wanted to make a more general statement. So we then studied how the relative contribution of line of sight halos and subhalos depends on the source and lens redshift, as well as the assumed halo and subhalo mass function. And so to understand this here, I'm fixing the halo mass function, and we vary the amplitude of the subhalo mass function, or this parameter F sub, which is the fraction of dark matter halo mass in substructure. So redder colors show that line of sight halos dominate, and bluer colors show that subhalos dominate. So pre-intuitively, we see that as we increase the amount of substructure, the colors go from red to blue. Now the question is, which of these three panels are we observing in practice? And we don't know exactly what the value of this parameter F sub is, but there are upper limits based on measurements of different systems. And we see from the values found in the literature that having a substructure fraction of about 2% is very unlikely for the mass scales that we are considering here. It is much more likely that we are in a scenario like this one over here. And meaning that the line of sight halos are dominating. And why is this important? Well, here I overlaid points that correspond to the bells over here and slacks families of galaxy-galaxy lensing. These are two well-known high-quality sets of lensing images. In particular, these are sets that have been used to place constraints on dark matter. And so we can use, we can see that for both sets, for a fraction of substructure that we think is more realistic, these systems are likely dominated by the halos along the line of sight. And so in order to translate a measured power spectrum amplitude to a dark matter theory, we think it is important to understand whether the subhalos in the galaxy or the line of sight halos are the dominant contribution to the power spectrum. Otherwise, we can obtain wrong inferences about the nature of dark matter. And the fact that under many lensing configurations and reasonable subhalo population assumptions, the line of sight halos contribution dominates the signal, we think that that's good news, because the subhalo mass function is very hard to pin down, while in comparison, halos along the line of sight live relatively calmer lives. How can we distinguish their effect? Well, if the perturbation is caused by a line of sight halo, the different planes in the problem cause a curl component in the deflection field. We can see here an example where the redshift of the lens, 0.5, there is no curl component, it's just noise. But as we move the interloper further and further from the lens, there starts to appear a non-zero curl component. And so in terms of current data, we are currently reanalyzing systems that were previously claimed as subhalos in the literature. And our markup chains indicate that it is likely that at least a number of them are halos along the line of sight. Here's one such example that was claimed to be a subhalo in a Nature paper. And these are results from a Markov chain over the parameters of the source, lens, and perturber. And we find that this system is indeed very likely to be an interloper. By this, I mean a line of sight halo, as opposed to a subhalo as it was claimed before. So this is a paper that we have under preparation, and it should appear shortly publicly. So let me summarize what I talked about until now. I showed you how we can use gravitational lensing to probe dark matter at kiloparsec scales, and this is a regime which so far has remained much less tested than the large-scale structure. I told you about ways to enhance direct detection with machine learning techniques. In particular, I presented methods that have comparable sensitivity to traditional methods, but are orders of magnitude faster. Once, of course, you have trained the neural network. I also talked about the statistical probe, the convergence power spectrum, which has the advantage that is sensitive to lower masses than direct detection, and it provides a more direct link to dark matter theories. So since our initial paper where we introduced our formalism for computing the power spectrum, there have been upper limits placed using strong lens systems, but there have not yet been a detection. Finally, I showed how we think that line of sight halos are the dominant contribution for galaxy-galaxy lenses, and this should be good news, in our opinion, or in my opinion, for our ability to say something about the nature of dark matter in an unbiased fashion. And so let me just finish by a little bit of a more broader picture. So today we talked about how we can exploit the information, or at least I talked about how we can exploit the information on small scales to gain insights about the dark sector. But we can, of course, try to learn about the dark sector at every scale using cosmological observations, from the cosmic microwave background to the large-scale structure of the universe, gravitational lensing, and other tracers of the matter fluctuations. And these are just some examples of work that we have been carrying out with my group in this direction. And this decade is really bringing a wealth of new and complementary data sets, and we will continue to exploit their complementarity and look for new ways of extracting information, and hopefully we will be able to shed even more light on the dark sector soon. Thank you.
Thanks, Cora, for this wonderful summary. I already see Matthias' hand raised. Go ahead, Matthias.
Great. This was an excellent talk, Cora. Thank you very much. I really liked it a lot. I was wondering, I remember Neil Dalal talking about using ALMA also for this kind of substructure in lensing thing. Do you know anything about that, and how would you think about going in that direction as well? Anything you can?
Yeah, so Neil and Yasser Hesave have detected one or two subhalos using ALMA. However, I know that Gil Holder has been working for now a number of years, perhaps 5 years or so, with a student trying to put limits on the power spectrum coming from ALMA. And it seems to be more difficult than he thought. I'm not sure what are the complications. I mean, they have to, they have to take into account the visibilities, but there have not been any progress on that domain so far. The limits that have been imposed on the power spectrum came from HST observations.
Thank you.
Great. Any, Rogerio, please go ahead.
Yeah, correct. So thanks for the talk. So when you go to very small scales, of course, you have to rely on non-perturbative, power spectrum is non-perturbative. So you have to rely on the halo model that you have introduced. And the halo model depends on the halo mass function and the halo profile. So my question is the following: in order to find out how those ingredients for the power spectrum change for different dark matter models, do you only have simulations to rely on, or is there any analytical way of making this map? And the reason I'm asking this is the following: suppose you have a limit for some exotic dark matter, say self-interacting dark matter, but then you have to fix the self-interacting cross-section. How do you get a bound on the self-interacting cross-section? For instance, if you change the self-interacting cross-section, do you have to simulate again or have an emulator? I don't know if my question is...
Yeah, I think I understand the question. I mean, we need to have at least the subhalo mass function coming. It doesn't coming from some sort of simulation. That's what we did in this work. It doesn't come from first principles. Just per se, we need some sort of simulations. What people have been doing, so for the SIDM or truncated NFW profile or whatever, dark matter scenario that you want to consider, is to run these very expensive, sometimes embodied simulations, sometimes hydro simulations. These are very expensive because they are very high resolution. An emulator for this particular purpose has not been used so far as I know. But yeah, I mean, people have, you can make, for SIDM, there are some scalings that it's not that you have to run a simulation for every cross-section that you want to test. There are some scalings that you can use, but in principle, for a different model, you will need the subhalo mass function coming from something like a fast simulation or a slow simulation up to now, but yeah. In fact, when I started doing this, I had in mind, what I first had in mind is to work out the power spectrum for fuzzy dark matter, a fuzzy dark matter scenario. It was, people were particularly interested. People have been interested. There are different waves, but anyway, people lately have been interested in fuzzy dark matter. But at the time, there were no simulations of the subhalo mass function. There are some simulations of fuzzy dark matter, yes, but not with particles. Yeah, I right now there is a subhalo mass function that has been worked out by Caitlin Schutz, so that can be done.
Right. And if I may, Sudhir, can I ask another question?
Please go ahead.
So there are questions whether you can make a kind of a challenge for this method to find things. So my question is, can you simulate using land astronomy or some other software? Can you simulate some exotic dark matter model and then try to use your tools to extract the correct dark matter model? Have you tried that?
You mean to simulate? Oh, to simulate. Well, so land astronomy is not going to. So I need to. Well, we could talk about what exact how is it called? data challenge you would like, but we need some subhalo mass function. We need to establish the subhalo mass function that should come from a simulation. But you're talking about using Lenstronomy to simulate a lens.
Yeah, lensing from subhalos from this mass function that comes from some exotic dark matter model. It's just a thought.
Could be done.
That'd be interesting to show that. Yeah. So you can show that you can actually extract and the correct properties. Well, that's great. Right. So thank you, Clara. That was a great talk. Thank you.
Thank you.
Any more questions for Cora? If not, thank you. Thank you very much, Cora, for this wonderful talk.